Okay, hi everybody. So now I'm going to go through one more example problem. This is Chapter 9, Problem 22. And let's just quickly read through it. We have some type of rotating cylindrical axle. Alright, so we have some kind of cylinder. And as this thing spins, has a rope attached to it. It's going to lift a 800 Newton bucket of cement from the ground to a rooftop 78 meters above. The bucket is attached to a hook to a cable that wraps around the rim of the axle. Right, so we have this rotating cylinder with some radius, so we don't know yet. And attached to this cylinder is a rope which is kind of wrapped around it. Right, we have some rope wrapped around this thing, and it's attached to a bucket. Okay, and as this thing moves, this whole rope is kind of being picked up as this thing spins in this direction. Okay, so you can see that happening in everyday life. So this is a real nice relevant problem. What do they tell us in the problem? They tell us the bucket weighs 800 newtons. So the weight of the bucket is 800 newtons. 800 newtons. They tell me that the distance traveled by the bucket is delta x. Let's call it delta y is equal to 78.0 meters. And that's all they tell us in the setup. And then in part A, they say, what should the diameter of the axle be in order to raise the bucket at a steady 2 centimeters per second when it is turning at 7.5 RPM? Okay, so as this thing turns, this rope is slowly being pulled up, and it's pulling up at 2 centimeters per second. So it told us a few more knowns here. Let's write those down. It told us the velocity of this rope and of the bucket as it moves up is 2 centimeters per second. And let's convert that to SI units. I'm going to multiply this by 1 meter is equivalent to 100 centimeters. Okay, so I end up with the velocity of 0.02 meters per second. All right, so this rope is being pulled up relatively slowly. They also tell me that the cylinder is turning at 7.5 RPM. Right, so since it's turning, revolutions per minute is some amount of angle every minute. Right, that's our angular velocity. Right, so our angular velocity is 7.5 revolutions per minute. Okay, so that's not an SI unit, so let's convert it to SI units. I have to convert revolutions to radians. I have to convert minutes to seconds. So 1 revolution is equivalent to 2 pi radians, right? Going around 1 complete revolution in radians, that is 2 pi. So I just need to convert this by using that conversion factor. 2 pi radians is equivalent to 1 revolution. Right, so when I do that, my revolutions cancel, and I end up getting things in radians. And then 1 minute is equivalent to 60 seconds. So 1 minute is equivalent to 60 seconds. So when I do that, my minutes cancel here, and I end up with radians per second, which is what I want. So 7.5 times 2 pi divided by 60, that gives me that the angular velocity of that cylinder is 0.785 radians per second. All right, so those are all just taking our given knowns and doing the necessary conversion factors. Okay, so now comes actually solving the problem. The problem wants us to find the diameter of this axle, right? So here's the radius. It wants us to find double that of the diameter of the cylinder in order for it to have this velocity and this angular velocity, right? So we know that the entire axle as a whole is spinning at some rate 0.785 radians per second, right? The velocity of each part of the cylinder is going to be different, right? The middle of the cylinder isn't going to be moving at all. A location here is going to have some velocity in this direction. A location here is going to be moving a little bit faster. A location here is going to be moving even faster. And right on the rim, there's going to be some velocity, right? And everywhere on the rim is going to have that same velocity. Right? And so that's what we want to find. Well, we know that. They told us that the rope is moving up at 0.02 meters per second, and therefore if it's not slipping on the cylinder edge must also be moving at 0.02 centimeters per second. So we know that velocity, and we know the angular velocity. Okay, so that means we need to somehow relate those two things, and we have an equation for that. V is equal to omega r. Right? If if I know my angular velocity, if I multiply it by my distance outward from the center, right, from the center of the circle to some distance r, that tells me my velocity at that location. So if I plug in r equals whatever this value is, that tells me the velocity at this point. If I plug in r equals this value, it tells me the velocity at this point. And in this case, I just need to plug in the radius of the cylinder, or that's what I'm actually solving for here. So to solve for the radius is v over omega. I know my velocity is 0.02 meters per second, and I know my angular velocity is 0.785 radians per second. Okay, so when I do that, I get this to be 0.0255 meters. Okay, so my seconds cancel, and radians aren't a real unit. Right? We keep it around because it helps with conversion factors, right? Just to make things kind of clear here, 2 pi radians is equivalent to 1 revolution. But in reality, we can drop radians when we need to because it's not really unit. It's really unitless, this measurement of the angle. Okay, so that's the radius, or I could convert this back into centimeters. This is equivalent to 2.55 centimeters. And so the diameter of the cylinder must be 2 times the radius, which is equal to 5.1 centimeters. Okay, so that's the answer for part A. Okay, for part B, and just note for a second that they told us the weight of the bucket and how far it was traveling. We didn't need that information at all. That was kind of extraneous information here to solve that. For part B, it wants to know if the axle must give the bucket an upward acceleration of 0.4 meters per second squared, what should the angular acceleration of the axle be? Okay, so now not only do we have a bucket which is moving up with some velocity, but now the bucket itself is also accelerating upwards. Right, so this is accelerating upwards at 0.4 meters per second squared, which means that this object must not only have angular velocity, right, but it must also be accelerating. The angular velocity must be increasing, right? So that's what we want to figure out here.